The hardware limitations of training large language models have long been defined by the physical size of a graphics card. For years, the industry standard has been that if you want to train a model with billions of parameters, you need a cluster of these cards working together. This is why building a state-of-the-art artificial intelligence usually requires access to expensive supercomputers or massive cloud infrastructure. It creates a high barrier to entry where only large corporations can afford to push the boundaries of what is possible. But a new research paper from April 2026 challenges this fundamental assumption. It proposes a system called MegaTrain that claims to train models with over 100 billion parameters on a single graphics processing unit. To understand why this claim is so significant, you have to understand where the bottleneck actually lives. When you train a neural network, you are not just storing the model weights. You also need to store the gradients which tell the network how to adjust, and the optimizer states which keep track of the learning momentum. In a standard setup, all of this data must fit into the video memory of the graphics card. Once that memory is full, the training process crashes. This is known as an out-of-memory error. The traditional solution has been to split the model across many cards using model parallelism, or to offload parts of the data to the central processing unit memory. But offloading to the central processing unit has always been too slow because the connection between the two chips is a narrow pipe compared to the internal bandwidth of the graphics card itself. MegaTrain approaches this problem from a completely different angle. Instead of trying to squeeze everything into the graphics card, it treats the graphics card as a transient compute engine. The heavy lifting of storing the model parameters and optimizer states is moved to the host memory, which is the main system RAM connected to the central processing unit. This allows the system to utilize the vast amounts of memory available on a standard workstation, bypassing the strict capacity limits of the graphics card. The researchers argue that with the right software architecture, the speed of the central processing unit memory can be leveraged effectively without creating a massive performance penalty. The engineering challenge here is the data transfer. Moving gigabytes of data back and forth between the central processing unit and the graphics processing unit over the peripheral component interconnect express bus takes time. If you simply copy the data every time the graphics card needs it, the chip will spend most of its time waiting. MegaTrain solves this with a pipelined, double-buffered execution engine. Imagine a factory assembly line where the workers are constantly busy. While one group of workers is assembling a product, the next batch of raw materials is already being moved into the station. In the context of the training loop, this means that while the graphics processing unit is calculating gradients for one layer, the system is simultaneously transferring the next layer of weights from the host memory. This overlap hides the latency of the data transfer and keeps the compute engine busy. However, there are significant trade-offs that the raw performance numbers do not fully capture. The system relies on full precision training, meaning it uses floating point 32 rather than the mixed precision formats like floating point 16 or brain floating point 16 that are standard in the industry. Full precision training is generally slower because the calculations require more data to move and process. The industry has largely moved to mixed precision because it offers a good balance between speed and numerical stability. MegaTrain argues that full precision is actually superior for model stability and convergence, suggesting that the slight slowdown is worth the gain in reliability. This is a bold claim that goes against the grain of current optimization practices. Furthermore, the reliance on host memory introduces a new set of constraints. The bandwidth of the peripheral component interconnect express bus is significantly lower than the internal bandwidth of the graphics card. Even with the double buffering optimizations, the system is still bound by the speed of that connection. In real-world scenarios, this can lead to communication bottlenecks that do not appear in controlled benchmark environments. There is also the question of out-of-memory errors on the host side. If the system RAM is exhausted, the operating system will start swapping data to the hard drive, which is orders of magnitude slower. This means that while you can train a larger model, you are trading GPU memory limits for system memory limits and potential latency spikes. The research team published benchmarks showing that for smaller models, such as 14 billion parameter variants, the system achieves 1.84 times higher throughput than the widely used DeepSpeed 03 framework. They also demonstrated the ability to handle context windows of 512,000 tokens for 7 billion parameter models. These are impressive numbers, but they come with a caveat. The paper acknowledges that the primary advantage is the ability to train without the need for model parallelism. This fundamentally changes the hardware requirements, suggesting that software-defined memory management and kernel fusion become more critical scaling factors than the raw count of graphics cards. Despite the promising results, there is a gap in the external validation of these claims. The available sources confirm the internal benchmarks, but there is a lack of comparative studies against other single GPU frameworks beyond the internal tests. Independent researchers have not yet had the chance to stress test the system against real-world failure modes like unexpected memory fragmentation or sustained long training runs. This creates a minor uncertainty about how the system behaves under extreme load. It is possible that the efficiency gains diminish when training for thousands of epochs rather than a few days. The system is designed to democratize access to ultra-large model training, allowing individual researchers or small teams to train state-of-the-art models on consumer-grade setups. But the engineering reality is that you are still paying a price in the form of slower compute cycles and higher system memory requirements. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.